Hi folks, we're going to take a look at the solution to page 364, number 17. Okay, so here we have a mass of 5 kilograms is suspended by two strings, 24 and 32 centimeters, from 2 points that are 40 centimeters apart and at the same level. Determine the tension in each of the strings. So this should look familiar. We've seen a question like this before, but we notice that the information that's given is different than the information that was given in the one we've already seen. Okay, so let's take a look at how we're going to solve this one, how it's different from the one we've already seen. Okay, so again, let's start by drawing ourselves a nice diagram. So they tell us that the strings are hung from the same level. Okay, so we use a straight line to show that. Okay, and again, my diagram does not need to be perfect, but I should be really clear in my diagram that one of the strings is shorter than the other. Okay, so this is 24, the other one is 32, and they tell us that they're 40 centimeters apart. And I've got my object here, which is 5 kilograms. Okay, I guess I could right away figure out what the force due to gravity is, since I know I'm going to need that. So 5 times 9.8, should probably be doing that in my head, but that's okay. So we know that the magnitude of the force due to gravity, so notice here I'm specifically giving the magnitude, is equal to 49 newtons. Okay, so I'm going to solve this using trigonometry, and even if I wanted to solve this using components, there's something I'm missing here. That's the information that's not given, that was given explicitly in the one we had seen earlier, is I don't have the directions for these vectors. So I know gravity is going to be downwards, but I have these two vectors which represent the tension in the string, and what I don't have is their is any indication of direction, in other words, the angles. Okay, so since I want to work with this triangle here, what I'm going to do is I'm going to find these angles in the triangle. But then, of course, using parallel line principle, I know that this angle here will be the same as that there, and it's going to help me give a direction for this vector. And similar, these two are equal, so help me for direction for that other vector. Okay, so first and foremost, before I even start talking about forces, I just need to determine these angles. Okay, so here, let's start with theta. Okay, so I have all three sides. I'm going to use cosine law. So that's its opposite side, so we know it's just going to be cos inverse of whatever its opposite side is, 32 squared, minus the squares of the other two, so 24 squared minus 40 squared, negative 2, 24, and 40. Okay, and let's calculate that here. So again, make sure when you're doing this, you're very clear about using all the brackets that you need. So I'm opening up a bracket for that numerator. 32 squared minus 24 squared minus 40 squared. Okay, close off the bracket, divide, open up a bracket for the denominator, negative 2 times 24 times 40. Okay, and we end up with 53.13. Okay, now I have enough information to use sine law to find the other angle, but because I'm going to be using two sides and an angle to find another angle, I know that that's the one that sometimes causes me the ambiguous case of the sine law problem, which I'd rather just avoid. So I'm not even going to bother checking to see if it's an issue or not. I might as well, the time it takes me to do that, I'll have already set up the cosine law. So here its opposite side is 24, so it's 24 squared minus 32 squared minus 40 squared, negative 2, 32, 40. Okay. So anytime I can avoid thinking about the ambiguous case, I will do that. So 24 squared minus 32 squared minus 40 squared. And here negative 2 times 32 times 40. Okay, and here we have 36.87. Okay. Okay, so now that we have our angles, we can now go ahead and solve the problem as we did before. So again, you can set it up with components and solve that system of equations to find the magnitudes of these two tensions. I'm going to solve it by adding these vectors tip to tail and using trigonometry. So here, I know that this object's at rest, so it's in equilibrium. So I should have a closed triangle, okay, to represent that the net force is 0. Okay, so here's my force due to gravity. I've already calculated its magnitude, 49. Okay, so let's start with this, with that string there. So I've got some tension, okay, that has an angle here of, what did we find for, that would be angle phi. Angle phi was 36.87. Okay, and then I know that this vector has to close off the triangle. Okay, so I'll call this magnitude of t. So that one there was the 32. So I'll call it t32. And then this other one here in the other direction, that'll be t24. Okay, hold on. An alarm just went off, so I will just turn that off. Sorry about that. And here, this angle theta, which we calculated, was 53.13. Okay, so what I'd like here is, well, I know this angle is just going to be, oh, actually I still have it on my calculator. So 90 minus that previous answer, oh, 53.13. Well, look at that. Looks like this is going to be actually a nicer problem than we thought. 53.13. Well, here, 90-degree angle, that means this has to be 36.87 as we have there. And in the end, we just have, looks like these are going to add up to 90 degrees. So look at that, we actually have a right-angled triangle. Now, my diagram doesn't look like a right-angled triangle, but that's okay. I wasn't necessarily anticipating it, and I certainly shouldn't have been assuming that it was going to be a right-angled triangle. Okay, so because it's a right-angled triangle, I actually do not have to use sine or cosine law at all. Okay, so let's find the magnitude of this vector here. So what I call t32. So if I take 53.13 as my acute angle, this is the adjacent side. So I have cos of 53.13 is equal to my adjacent, which is t32. 32 there, over my hypotenuse. Now that 49 actually becomes a hypotenuse, so the magnitude of t32 is equal to, what do we have? We have 49 times cos of 53.13. Okay, so 29.4. Okay, so here 29.4. And that's newtons, and then it'll be similar for T24 because that's just going to be using sine since it's opposite to that. So we have the T24, its magnitude will just be, and I'll do it all in one shot. I know it's going to be 49 times times sine of 53.13, and so here, what does that give us? That's 49 times sine of 53.13. Sorry, I don't know why I wrote 17 here. It's supposed to be 13. Okay, and that gives us 39.2. Okay. Now, I suppose here, since they hadn't given us the direction, I guess we should give here, so we'll say T32 is equal to 29.4 newtons, and we have to describe the direction. So here we'll just say, whatever it was, phi. So that's 36.87 degrees from the wall, or sorry, from the ceiling. Okay, so 36.87 degrees off the ceiling. There you go. I guess that's good enough way of describing it. And then T24 is going to be equal to 39.2 newtons. And this one here was represented by angle 53.13. So this will be 53.13 degrees off the ceiling on the other side. Okay, not the most, not the nicest way of putting it, but it gets the job done. Okay, so just to recap this one here, there was a whole set of calculations we had to do before starting. We had to first determine the directions of the two tension vectors, which we were able to do because we had the lengths of the strings. Okay, but again, notice the lengths of the string don't necessarily represent the magnitudes of the vectors. Okay, we happened upon an interesting little scenario where this triangle turned out to be a right angle triangle, so that meant I didn't actually have to use the sine and cosine laws. Okay, that's it for this one.